All right, let's solve some questions about trig functions using trig identities. Now, if you don't remember the trig identities, that's fine. No one does. Look up trig identities in Google or something like that in your favorite search engine, and look up the like images, and typically you'll find a compilation of the important trig identities. If you were to have a textbook, like a physical textbook, typically in the front or the very back, like the just open up the cover, and you're going to see a bunch of listed identities for those things because there's so many that they're not really expected that you memorize them. Now, what is sine alpha plus beta and cosine alpha minus beta if we know this is the case and both of these are contained within this interval, which is the second quadrant? Okay, so for this we know that sine, the sum identity for sine. Looking at the identity itself, we get sine alpha cosine beta plus cosine alpha sine beta. So we can see we already know what sine alpha is and cosine beta is. So we already know sine alpha and cosine beta. We do not know cosine alpha and sine beta. So we need to find those. To do that, well, we can just create a right triangle out of this, right? Sine alpha equals 2 over 3. That means we're in the second quadrant, so I should actually draw it kind of like this on the unit circle. This is going to be alpha. Sine is opposite over hypotenuse, so opposite is 2, hypotenuse is 3. That means the third side here is going to be, let's see, 3 squared minus 2 squared equals, I'll name this x. We get 9 minus 4 equals x, so this is x squared. That means x equals the square root of 5, and specifically it's going to be negative root 5 because we are in the second quadrant, which means it has to be a negative. It's going in the negative direction. It's not negative because this is a distance, but for the purposes of our understanding the signs, it's going to be helpful to have that there. Now, likewise for beta, beta is also in this side here, so this is going to be beta. It says cosine is negative 1 over 4. We know that cosine is negative in this, so I'm going to make this adjacent over hypotenuse. I'm going to make this negative 1 over 4 for the hypotenuse. So using this, it's going to be 4 squared minus negative 1 squared equals, I'm going to name this y. Y squared is going to be 16 minus 1 is 15 equals y squared. And that's, of course, going to be positive root 15. Because the negative 1 handles the quadrant we're in. Okay, so that means that sine alpha, we already know that, 2/3. Cosine beta is negative 1/4. Cosine alpha is going to be, let's see, adjacent over hypotenuse, so negative root 5 over 3 times sine of beta is going to be opposite over hypotenuse, root 15 over 4. Negative 2 over 12 plus, or actually a minus, root 75 over 12, which is just this is the same thing as 25 times 3. So we're going to get negative 2 minus 5 root 3 over 12. Okay, so we're going to now look at cosine alpha minus beta. That's going to be cosine alpha, cosine beta, plus sine alpha, sine beta. All right. Cosine alpha is negative root 5 over 3. Cosine beta is negative 1/4. Sine alpha is 2/3. Sine beta is root 15 over 4. Negative root 5 over 12 plus 2 root 15 over 12, which gives us 2 root 15 minus root 5 over 12. So a little bit of work for this one, especially with those reference triangles that we needed to create, but that's how you can do it. Now, to verify the identity, you can do it multiple ways. You can do, the left-hand side, simplify that, right-hand side, move things around. I'm going to rewrite the left-hand side because the double angles, I think, are easier to change into a single one, right? This is going to be a little bit more difficult to make into a double angle using just this information. So let's work with this side here. Using the double angles, cosine is going to be and at this point I can distribute. I can distribute the first term into the second one. Same thing with that. This is really the same thing as that. So we're going to get cosine squared x, cosine squared y. Then you can see that here we have the same term, but we're doing the different sign. That's the same thing as multiplying by the conjugate. And that means that the cross terms, cosine x, cosine y times sine x, sine y, minus sine x, sine y times cosine x, they're going to have, it's the same thing but different signs, which means they cancel. So you don't actually have to calculate this term times this one and this term times this one. All we need to do now is calculate this one times that one. It's going to be minus sine squared x sine squared y. And we know we want to have cosine squared x minus sine squared y. So to do that, I'm going to change this sine squared x into cosine and this cosine squared y into sine, because I want to have sine to have y, cosine to have x. So this becomes cosine squared x is the same. This is going to now become 1 minus sine squared y. Then I'm going to have 1 minus cosine squared x. Change that one over here. And then sine squared y is going to remain the same. Okay, we can simplify this a little bit, I believe. Let's distribute this, distribute the negative and the sine. That's going to give me cosine squared x minus cosine squared x sine squared y minus sine squared y, then plus cosine squared x sine squared y. And you can see this and this cancel, giving us cosine squared x minus sine squared y. That's exactly what we want. That's this statement right there. Okay, give it a try in number 3 and 4. All right, simplify the following into a single trigonometric expression. And for this one, we really want to look at what is given to us and see if there's a trig function that satisfies this whole thing. And there is one, actually. I can see that sine 2 theta equals 2 sine theta cosine theta. And that looks to me very similar to this. Now we don't have 2 sine theta cosine. We actually have 2 times 2 sine theta cosine theta. So that tells me that we have 2 times sine 2 theta. Theta in this case, of course, is pi over 8. That's going to give me 2 times sine pi over 4. And this, of course, you can actually evaluate. This evaluates down. You could have evaluated there, but this evaluates down into 2 times root 2 over 2, which is just root 2. But that's not what they wanted. They wanted a single trig expression. And so that would be the correct solution. Okay, verify the identity that cotangent minus tangent equals 2 cotangent 2x. Let's see. I think I'm going to try taking cotangent and write it as cosine x over sine x minus sine x over cosine x. I'm going to try and change this into 2 cotangent. This should look like 2, let's say sine 2x over cosine 2x. That's what I'm expecting to find. Okay, now let's get common denominators. So we're going to multiply by cosine x, sine x, sine x. That's going to give me cosine squared x minus sine squared x on top over sine x, cosine x on the bottom. Okay, I know I'm looking for sine 2x and cosine 2x, so I need to have a double angle in there somewhere. And looking at the double angle formulas, actually, I see this. I see sine 2 theta equals 2 sine theta cosine theta. We just used this one in the previous problem. And I see that cosine 2 theta equals cosine squared theta minus sine squared theta. I just realized that this is actually supposed to be cosine over sine. It's cotangent, so that's what we get. And this is exactly what we want on top here, right? Cosine squared minus sine squared, cosine squared minus sine squared. I can rewrite this as cosine 2x on top. And on bottom, I have sine x cosine x. Well, that's right here. Sine x cosine x. But I have this 2, so I'm going to divide the 2 over, and I'm going to get sine 2 theta over 2 equals sine theta cosine theta. So that means that this is going to be sine 2x over 2. Division by a fraction is multiplication by the reciprocal. We're going to get 2 times cosine 2x over sine 2x, which is the same thing as 2 times cotangent 2x. And that's exactly what we wanted. So once again, looking at what is given to you, keeping your head in the game, asking, do I see any identities in this that I can use? Always keep in mind what you're trying to do. So here we did not have any double angle on the inside. At this point, I looked for double angles because I saw some similarities to things that I recognized, but I know I wanted double angles in there. And that's what the double angle formulas really led me to. So that's how I recommend handling some of these types of problems. All right, it says find the following expressions with the given triangle. Now, we can't really find anything else about this triangle unless we know the entirety of it. So I'm going to use right triangle trig. That's going to give me 36 squared plus 77 squared. Plug in a calculator, 36 squared plus 77 squared then taking the square root of that. It's going to give me 85. Okay. Now, cosine of 2 theta, we want to find what is this thing equal to. So cosine of 2 theta equals a number of things. We can do cosine squared minus sine squared, 2 cosine squared minus 1, 1 minus 2 sine squared. I'm going to do 2 cosine squared theta minus 1 just for something more unique. So this one says this is theta here. So cosine of this is going to be adjacent, 36, over hypotenuse, 85. So we're going to get 2 times adjacent over hypotenuse squared minus 1. And we can simplify that down. This is going to be 85 over 85. Actually, I need to have the squared version of that, so it's going to be 7225 over 7225, which gives me 36 squared times 2 is 2592 over 85 squared is 7225. That's going to give me if you double theta, this is going to be a bigger angle. It's actually going to end up being, if you plug it in, do the trigonometry, it's going to be about 65 degrees. And if you double that angle, you're going to be have an obtuse angle, which goes into the second quadrant. So cosine in the second quadrant is negative, which is why we got a negative here. All right, for sine of phi over 2, phi is this angle down here. And we want sine of phi over 2, it's a half angle. Well, let's look at the half angle formula. Now, half of phi is already an acute angle. It's already in the first quadrant. If you take half of it, it's going to be just in the first quadrant again. So we know that we're going to have the positive version because we have the choice of plus or minus. I'll show you that here. Sine of phi over 2 is going to be plus or minus the square root 1 minus cosine phi over 2. And like I said, we're going to have the positive version, not the negative. We're going to be still in the first quadrant. So simplifying this, we're going to get cosine of phi. Cosine is going to be adjacent over hypotenuse. So 1 minus 77 over 85 over 2 and the square root of that. So 85 over 85 is the same thing as 1. Minus 77 is going to be 8 over 85. Then divided by 2 is going to be 4 over 85. And the square root of top and bottom is going to be 2 over root 85, which is the same thing as 2 root 85 over 85. And that's our answer for that one. Okay, tangent of 2 phi. So tangent of 2 phi is going to be 2 tangent of phi over 1 minus tangent squared of phi. So tangent of phi is going to be, let's see, opposite over adjacent. So opposite's 36, adjacent 77. So we get then 1 minus 36 over 77 squared. Okay, we're going to get, see on top, we're going to get 72 over 77 on bottom. Let's see, 77 squared. We're going to get 5929 So we get 72 over 77 times and we can reduce. We get 5, 5, 4, 4 over 4, 6, 3, 3. Not sure if that can reduce any further, but that's what I got for tangent to phi. All right, reduce the powers until there are no exponents higher than 1. And we have sine to the fourth of 8x. We just need to reduce sine. So first off, we can use the power reduction formula. For sine says, for sine squared, this is really the same thing as sine squared 8x squared. Sine squared is going to be 1 minus cosine of 2x. In this case, x is 8x, so we're going to have 16x here over 2, and that's going to be squared. So we need to multiply this thing out. So it's going to be 1/4 in front. We have 1 minus 2 cosine 16x plus cosine squared 16x. And this can be further reduced. So let's use the trig reduction for cosine squared. Cosine squared says we still have the 1/4, 1 minus 2 cosine 16x. Then we have cosine squared is the same thing as 1 plus cosine twice the angle. 16 is the angle, so we're going to have 32x over 2. And that's actually reduced. So we don't actually have to go any further than that. We could multiply things out, but that only has exponents of 1 inside of it. All right, verify the identity, this thing here. So now I want to have 3x here. And what that tells me is that maybe what I want to have is 2x plus x. And that's important because 2x is what we just saw with the power reduction formulas. If we have a squared power, we can reduce it down to a double angle. And that might be important in this case. I'm not sure, but it might be. Now, for cosine to be that, we know that this sum is going to be cosine 2x cosine x minus sine 2x sine x. Okay, for this one, I'm going to look at using expanding this right-hand side. Instead of working with the left-hand side, I'm going to expand the right-hand side and see if that makes it a little bit easier. So I'm going to use this idea. 3x is the same thing as 2x plus x. So I can expand it like this. Okay. Once again, when I do that, I'm looking to get this side as a result. So cosine 2x cosine x. Well, I already have that cosine x. That's good. If I can find a way of getting an extra 2 power of 2 here, then that will combine into my cosine 3, cosine to the power of 3. And then we have sine 2x and sine of x. So first off, I can see there's no 2x's in there. So let's use the double angle formulas to simplify. So I find that cosine 2x, I'm going to write it like this. I'm going to write it as 2 cosine squared x minus 1. I'm going to see if that works. I may need to use a different formula because there's actually a few of them that I can use. And then sine squared, or sorry, sine 2x is going to be the same thing as 2 sine x cosine x. And we get sine x there. So let's distribute the cosine and see what we get. We're going to get 2 cosine cubed x minus cosine of x minus 2 sine squared x cosine of x. And I'm really close now. This is correct, and we have this is correct. We don't have the correct numbers. We want to have this 2 gone in the front here. This needs to be gone, and this needs to be 3. So let's see what we can do with that. I'm going to split this up so we have cosine 3x. And I'm going to move this over in front to be minus 2 sine squared cosine squared. This just makes it a little bit easier for me to see what I'm working with. I split this one up, so it's going to be plus cosine cubed x minus cosine of x. Now I need to have one more of this, so what I'm going to do, I'm going to change one of these cosines. So this is the same thing as cosine squared x cosine. And I want to have sine squared in there. So I'm going to make this, use Pythagorean identity to change this to sine, it's going to be 1 minus sine squared x times cosine of x. Then we have minus cosine of x. I could factor out that cosine, and that would give me 1 minus sine squared x. Let's see, minus 1 cosine of x. I distribute that back in, that gives me there. And this becomes, let's see, 1 minus 1 cancels. We get negative sine squared x cosine of x. That's exactly what I want. I want negative sine squared x cosine squared of x. So I get cosine, this whole thing just becomes cosine cubed x minus 2 sine squared x cosine x minus sine squared x cosine x. Those add up to give me cosine cubed x minus 3 sine squared x cosine x. That is exactly what I want. I want that to give me this. So I changed this thing in using this formula, and I managed to make the left-hand side of the equation. So I've verified the identity using these identities here. A little bit tricky because instead of collapsing, which tends to be a little bit cleaner, I think. This one I felt like it was easier to expand the cosine 3x out. It's just you see the identities that you can use to get there. Okay, give it a try in numbers 5, 6, and 7.